All right. So the project promotes knowledge, environmental awareness, and skill development among participants. At the same time, it strengthens cooperation between European higher educational institutes. We have here three universities and also another institute related to pedagogical ideas and facilitates the exchange of expertise internationally, contributing to integration of new interdisciplinary methods in geoscience research and teaching. So it is not only the workshops that you are following these days. There are some tools, some open tools that you may use. Either you are a student or you are a tutor or a researcher that you may find interesting, not only as a tools, but also the material we have uploaded over there, which is open for everyone. It is a great pleasure to host you here also today. This series, it is not just sharing knowledge, it is about creating connections, asking questions, inspiring actions and young researchers. So at the end, we have also the opportunity to discuss. And even if it is not happening right now, if you don't have the time or if you have a question later on, we are here. You have our emails. It is very easy to find also the consortium through the webpage of our project. Please do not hesitate to contact us. We will be very glad to keep this discussion alive. Thank you once again for joining us, and I hope you find also this third workshop interesting, inspiring, and a beginning of new ideas and new collaborations. Now it is time to give the floor to our first speaker, who is Alexandros Liaskos. Alexandros Liaskos is a geologist and a researcher at the Department of Geology and Geoenvironment of the National Kapodistrian University of Athens. He specialized in geoinformatics and coastal geomorphology, while he is actively participating in different and various European research projects. He has a long experience in the development of scientific applications as well as digital tools and algorithms. Alexandros Liaskos is one of the Greek members of TRACE project. Alexandra, the floor is yours.
Thank you very much. Hi from me. Should I start sharing my screen?
Yes, please.
Could you confirm that everything is fine?
Yes.
Yes.
Perfect. Good afternoon, everyone. It's a pleasure to be here with all of you today, and thank you for the opportunity. For the presentation of today, I will be talking about GIS and drones. As Mr. Elpidu told, um, I have already worked with geospatial analysis and with geoinformatics and remote sensing, so I have a little bit experience in that and from the part of research in the university. So we will be mainly focusing on mapping ship from the sky. And what that means is that we will be discussing about the environmental changes and how we can monitor them from drones. And we will also focus on a few examples and some case studies and workflows that are mostly popular. So let's start. First of all, what's drones? Drones are actually the unarmed aerial vehicles, which, as the name suggests, it's without humans inside these vehicles. So it's not like planes or anything else like it. And they're used in many fields of science and not just science. They're used in military, they're used for public safety, agriculture, for scientific research, media, and many more. So the vehicle, it can operate either um, from remotely operating by an operator or even autonomously without even a human controlling it. Um, About the equipment, well, that's the most important thing, I believe, because in drones, you can uh, attach any kind of sensor that you want for your own research. For example, it could be either just simple cameras, it could be expensive high-end cameras, it could be scanners like it could be radars. Uh, and from the electromagnetic spectrum, it can be even thermal or any kind of multispectral sensor. And what's the advantage of drones? It's that, well, first of all, they can be used in our own by our own will. So it's whenever we want, wherever we want, and however we want, with whatever um, sensor we want to attach. And also, it's very important to mention that they are um, very safe in terms of environments that are dangerous and hazardous. For example, in high altitude glaciers, if you want to make a field survey, it will be very dangerous to do it yourself. So drones are a lifesaver for such kind of cases. And also they offer high resolution data, and they can be flown below the clouds, so we don't have cloud interference in our results. So now let's follow to what they are actually used for, which is which are actually there are actually many cases, but we are going to focus on the main ones. First of all, it's the infrastructure inspection. For example, here you can see an oil tank being monitored from above. Um, I'm not sure how this research and monitoring is made, but it's a very popular among researchers and companies and agencies. Now let's follow to precision agriculture. It's called. It's actually agriculture, but with smart crops and very high um, very high resolution in order to be able to selectively know um, as an individual who has maybe the field what's going on with your own land. And for example, in the image you can see that's an NBVI, it's called. It's an index. It uses many uh, bands, which are not the red, green, and blue of the true color image that we know, and that very useful for detecting vegetation. But we're going to talk a little bit about this maybe in um, later. So now it's also about search and rescue, and that's a very important thing in maybe military operations because you can use not just static images. Here we can use live video, real-time video, and we can use algorithms and machine learning for object detection and to be able to track and monitor even the movement of, let's say, people, cars, or whatever else. And that also works with thermal, which is very important in the dark. And now to the most important one, we're going to talk later about all these things too, but it's environmental monitoring. And here in the picture, you can see a digital surface model, which is like a digital elevation model showing, but it's showing also not just the bare earth height, elevation, but also from the objects on top of the earth, like buildings and whatever else it could be. So that's in addition over the digital elevation models. And mapping and serving, the most high-end tech for mapping a 3D environment. It's a LiDAR, it's a radar that is used for incredible precision, and it has some advantages over uh, the uh, the multispectral sensors, but it's more expensive. It's more it's not that common actually in research. And last but not least, we also have the delivery. So we see today that the drones have started even to be used as a delivery system, and that's also maybe use case. So we're gonna focus on UAV. That's the unarmed aerial vehicles based spatiotemporal monitoring. Spatiotemporal means that it's both uh, about space changes that happen and spatial changes, and also about temporal along different dates and times. And we're gonna focus on the environmental dynamics, meaning the changes that happen, but in the environment. And here you can see some of the ways that the data that we can use, as we said before, it's RGB, that's a true color image, it's LiDAR, multispectral, different indices, the thermal, and also oblique from a side view and not an orthophoto. So now we will try to understand what actually an environmental change detection is, because as you can understand in an image, in a drone image, we can see many kind of changes. But there is a difference between transient phenomena and environmental evolution. And what that means is that transient phenomena, it's everyday case uh, objects and changes that can be viewed in an image. For example, here you can see 3 cars being detected, and in a later date, they're not present. So that's a change we have detected, but it's not what researchers in most cases are aiming for. Um, so what we're aiming for is the environmental cases. For example, here you can see that's in a coast, and what you can see, the change you can see, it's coastal erosion. So there was an event and something happened, and you can see that the area has completely changed. And what has happened, we will talk about this one specifically later. So how to monitor change? There are a few ways, the most popular ones. First of all, it's about volumetric changes, changes that happen in the height, in the elevation. And that can be done with what's called a depth of difference. So it's about having more than one digital elevation models, and we subtract them in order to find the difference in the elevation. Also, it's about the kinematics and future tracking, about the motion that can be detected from drone images and data. And well, we're not going to focus that much on this one, but it's very useful. And there is also the case of indexes, spectral differencing, as we said before, with the NDVI, and that's mostly used for vegetation, for the plant health, and even uh, burn cases, burn severity from fires, forest fires, for example. And there is also the categorical, which is mostly about machine learning and about detecting specific objects and how they have changed among the the images that we have. So what's the most important thing in about detecting a change is that you can't do it from one single kind of data, one image, for example. It has to be more than one. It has to be uh, at least two, because we have an event and we have to have a prior to to an event data and post after the event data. And that's why I selected for the workflow that I will present you today, this research that had available data to be downloaded. So that's the map that you can see on the left. It's from Goose Rocks Beach in Maine, in the United States. And this map shows the changes that occurred, the coastal erosion that happened during a storm event in the winter of 2024. And the researchers used the dam of difference that we talked about before in order to compute the difference and find the erosion that happened. And so uh, what you see here, that's a small area. We What I actually did is that I focused on a small area that I could work upon, and I first digitized the anthropogenic um, and other kinds of non-environmental objects that I could find in the image, which, as you can see, it's some roads, some cars and buildings. And you might ask me why is this important? Because in the abstraction of digital evaluation models, it's not that easy to be done. It has to be done in a more analytical way, and you have to use some objects that are going to be constant and that are not going to change between the two images that you have, and these are going to be like your constants. So I use these ones, and I digitize them, and then I use the two DEMS and also an algorithm from Newton CAB for that's for core register. It's for the shifts for the because the two DEMS might have differences and you have to align them. So that's a very popular algorithm that's used from everyone, and it did the same. And we will also share some images from that research later. The next one, that's another kind of um, research that uses drones. It's not about um, digital dams of difference or anything like this. It's a very uh, strange one. It used some advanced techniques, and what happened here is that in Canada, in Alberta of Canada, you can see in the map over there on the left, uh, there are some forests of coniferous and boreal forests, and there was a gas pipe that had been um, had been added in the region, and they had to cut to destroy the forest on that area. And that area is the horizontal one that you see that there are some weird colors as you see right now. Um, so the researchers wanted to estimate how much it would take, or if it indeed is happening, uh, for the forest to regenerate in that area that was cut. So what they did is that first of all they used the drone images, and from the drone images they used photogrammetry in order to take the digital elevation model, and then from that they computed the ELSA score. ELSA score is it's something where it's an entropy based a local indicator of spatial association, it's called. What it's actually, it's showing how complex the area on that specific place is. And using that, they were able to compute if in that specific area, forests are going to be regenerated or not. And the complexity was showing if the plant was uh, different or the same on that area. That's what complexity means. And that plays a crucial role on from their own workflows and knowledge. I don't have this knowledge, but that's what they say and that's what they did. Um, so now let's move forward. Now about floods and disasters, that's another case. It's um, it's different from the vegetation and the coastal erosion that we had before, but it's also a disaster like coastal erosion. And so here you can see that the researchers used um, a lot of input data. Uh, First of all, they used some multispectral indices, and they used the true color image. They used the digital elevation model, and from all of this, they were able to get the water surface area. That's the WSC that you see on the second row, and as they got the water surface of the flood event that had occurred from all of the data, of course, were for drones. It was both the digital elevation model, which occurred from photogrammetry that they used to get the high elevation, the high resolution digital elevation model. And for you that, because I didn't mention it, this kind of technique, it's that because in drone photos, you don't just take one or two photos, you take a lot of them, and they have um, some um, some common areas between them. They have overlaps, and both in all directions. So this overlap is being used in order to get the height in the area of the overlap. It's technique used. It's very popular, and it's one of the most important advantages of drones, that you can get digital elevation models that easily. So so they got the water surface extent, and then they used the bare earth elevation from the Thames, and um, what they did is that they also used a TIN, it's a triangular irregular network. They just got the places where water was zero, which is the edges, uh, that the edges of the flood, and combining this with the dam, they were able to calculate the exact water depth at every single pixel. So that's the different thing that they were able to do. They were able to detect depth of a flood of the water just from drone data. And below, you can see in the big map, in the last image, that's the flood water depth map. And the blue water shows the depth. The darker, the more deep the area is. And now the last one is about clusters, and but it's not. It's a very interesting research because it was made on debris-covered glaciers. If you don't know what's that, um, that's what happens in glaciers where when we have soil and rocks deposited in high altitudes above the ice that there is from the glacier, and among years as it flows towards the uh, low elevations, it's being deposited on top of the ice. So you have rocks. Above rocks, you have the glacier, the ice, and above the rocks, above the ice, you have again uh, rocks. So you might think that in that area there is no glacier, but actually it's below the rocks. So here in this map, you can see it's from the Italian Alps, from the Belvedere glacier, and the researchers took data from drones from 2015 for from each year up to 2020, and they didn't in order to compute if the glacier is losing ice or not. So here you can see that's the area where the glacier is supposed to be, but as you see, there is no ice. But over there, you can see those two small areas. That's actually the ice that it's being revealed in this place because the debris that's on top, it's not that thick. It may be from a few centimeters up to a few meters, and that depends a lot. And we will see. We'll talk uh, why it's that. Okay, so here are the orthophotos that we're taking for each year. And it's very important to see that in the first orthophotos, if it's visible to you, you can identify some ice, and you would think that this is from the glacier, but it's actually not. It's because it's winter and snow had sat on top of the debris. So what you see over there, it's not the glacier. So how do you detect the glacier loss if it's not even visible from orthophotos? And that's where the the digital elevation models are again useful. And as you can see, in one more case, they are being used. So they are used a lot in research, and drones gives us the ability to have such data. So that's another a crucial advantage of them. Um, so here you can see that's the data that they collected of the elevation among the years. They had, you can see below some cross profiles, um, and above them it's there are charts. And what's visible is that uh, in almost uh, in most of the areas there was a loss of 20 meters of 20 meters height, 20 meters elevation of ice being lost in a period of 5 years, and that's a lot. And why is this happening? That's the the factors that um, the factors that play a significant role in in the phenomenon are, first of all, the the height of the debris, because if it's just a few centimeters, uh, then it's being like um, it melts more the ice. It's not working as you would suppose to be um, like protector of the ice because of the thick layer. But because the rocks are darker than the ice, and they don't reflect that much of sunlight, they trap heat and that melts the ice. So that's one of the factors. And the second one is um, it's the rising temperatures of climate change. So they want to see how climate change is affecting ice loss in covered glaciers. And over here in the zoomed in area, you can see that it's almost 20 meters. And now let's go again back to Maine, to the Goose Reef rocks bits. As I got the data from that research, the original data that the researchers used, I was able to redo the workflow. So over here you can see that's the orthophoto from the area prior to the event. And I have selected this small area that you see on the top, and later we will work. I worked in that one. So here you can also see um, that's the hillside of the digital elevation model. So before we had the orthophoto, actually there were multiple orthophotos taken from drones, so we were able to get the 10, and from that you can use the hillside in order to see changes much easier to the human eye. And that's the orthophoto from after the event. And from here, with the eyes, you can see that much change, although later we will see a little bit of that. But you will understand what we're gonna do. So here's also uh, the hillside of after the event photo. And right here you see on the zoomed area, the two orthophotos, it's visible that there is some kind of change. And you can see on the right one that indeed there is something more towards the land. First of all, what you see here, it's not the water, the gray area. It's actually the wet sand, uh, because it was in an intertidal period. And but you can see the change that happened to the beach, to the coast, what the storm event caused. And here it's also the hillsides, and in the hillsides it's a little bit more visible changes, but they are not as we would want them to be. So over here, first of all, what I did is that in GIS, I was able um, to digitize the constant areas that we talked before, the buildings, the roads, and everything else that I could identify as not a changeable object. And also we I tried to not to let out any form of water from the sea, because that affects the workflow, because it's not going to work if you have water. It's going to give out some fake mock results, and you're going to see maybe erosion or deposition, but it's not going to be any of those. And that's the final outcome. But here it's uh, the erosion and deposition and erosion and accretion happening from the story event. Of course, we don't see an accretion; it's only erosion. Um, the red areas. The white areas is where there were no change, and the black areas is with no values. Um, and as you see, we left out the uh, the buildings and the roads, and we used the algorithm that I told you before because we had to align the two digital elevation models, and then we subtracted them, and we were able to get the result of what actually happened to the area. From and if we had tried to use maybe satellite data or field survey, it would have been it would have been worse. The result, not that cheap, not that easy, and as you see, the resolution is extremely high. So it was a win-win. So thank you, everybody. That was what I had to show you today. I hope you were able to follow me and we understood most of the things that I said. Also, I want again to thank you for the opportunity that I had to be here today and present among all of you. And I wish you to be a researcher in the future too, because that's something I love, and I think you would too. And um, I leave the floor to the next speaker. Thank you very much.
Thank you, Alexandros. It's very interesting what you shared with us. We don't have time for a discussion right now, but if you have something that you would like to ask Alexandros, don't hesitate to write a chat. Alexandros will follow the chat and reply to you. Otherwise, at the end, we will have some time for all the three speakers. And now I would like to present the next speaker, Alfred Vespremenu Stroe. I was never able to say your full name correctly, Alfred. I'm sorry for that. For those who joined our workshops the previous week, you have already met him. For those that you are your first time today, I will say that Alfred Vespremenu is a professor of physical geography at the University of Bucharest, and specifically Faculty of Geography, and he is the head of the Marine and Fluvial Research Station of the GEODAR Research Center of Geomorphology, Geoarchaeology, and Paleoenvironments. His research is focused on coastal processes, geomorphology, paleoenvironmental reconstruction, geoarchaeology, climate change, and periglacial processes. Alfred is a part of our is a member of our TRACE project from Bucharest University. Alfred, the floor is yours.
Thank you very much, Nikki. Good evening to everybody. So last week we had a talk using sediments for reconstructing or trying to reconstruct paleogeography during the Holocene in the Yalova, Voidochilia lagoon system. And today we are coming back to the roots, to the methods. So this is the title I will present. It will be a relatively short presentation concerning the coring, how we core in the field and how we use the sediment after that in the lab. So certainly we'll have time for questions. I hope will be some. And is it visible maybe the screen now? What do you think?
Yes, it is.
Okay, so it's still,
Now it's perfect.
yes, very well. So first about scoring, and second about the kind of analysis. But also it's important from the beginning to have a short introduction concerning the value, the importance of the sediments, and finally why we are using sediments for our reconstructions usually. And I think this figure shows different kinds of sources, data sources, and also the time span of the record. And from basically instrumentally data, which normally cover a few decades or 1 2 centuries, if we are speaking about the sea level or um, climatic data, then we have the historical one, which are in some old newspapers, in old maps, sometimes, especially in the Greece, in historical references concerning some information about the environment. Otherwise, are the tree rings. You know that the tree normally capture information for some centuries, but using also fossil wood, we can have a longer time span for the tree rings, covering sometimes even millennia. And then are the beautiful ice cores. Uh, the only wrong point with the ice is present only in the polar and subpolar regions and in the mountains. And in the mountains usually is not so thick, not so old. Otherwise, even the ice capture a lot of information, but not all information. It is not better than sediments, but it's better for doing, let's say, isotope analysis, because oxygenium and hydrogen, deuterium especially, it's well present in every water molecule, and you can derive easily isotopes for paleoclimate using ice. Otherwise, we have the sediments in different systems. We have in floodplains, in marshes, in lagoons, which is just another type of lakes. And of course, we have on the ocean floor. And all these kind of sediments are very, very useful for reconstructing. We may compare the sediments with the pages of a book. It's difficult to read, but it's one of the few that the nature let for us to decipher, to try to decipher and to, let's say, rewrite. So we use sediments like one of the best way to capture information about the past in different meanings. But today we are speaking about the natural environments, of course. And I just given an excellent examples of the power of the sedimentary archives with a well discovery which happened 10 years ago, when during the famous ocean drilling program, which is in charge from the 1960s, covering all the seas, succeeded to take this kind of marine borehole, um, capturing the moment happening 65 million years ago, when a huge asteroid impacted the Earth near the Yucatan region, and producing the last mass extinction in the world, and normally favoring the development of the mammals and the humans. And in this case, the key horizon was the presence, of course, of different kinds of volcanic gases, ashes, and the differences in the life that was captured before and after this impact. So this is a very nice impact signature in terms of stratigraphy and geochemistry and the magnetometry, but otherwise is the paleoecology, looking and comparing the before and after life in the ocean especially, but also in the pollen captured from the continents. And we could see how many species disappeared at this time. So just an example what powerful it is, this method. Otherwise, usually we are using floodplains, lagoons, lakes, simple lakes, and they are nice environments capturing information about climate, about soils, geology, about morphological processes also. We'll discuss later how we can find information, reconstruct information about the morphological evolution, and very important also about the human history. So it's a very powerful tool to find new information about history and archaeology using sediments. We call it geoarchaeology, and it's one of the most powerful way to bring new data in archaeology nowadays. Of course, lakes are also useful environments for pollution, for historical pollution also, or for different biogeochemical cycles like the carbon cycles, which is so important for the climate changes in the present. So I make a list with the proxies that we are using in a borehole. Then we'll detail later, but now just to have an full image. So first of all are the sedimentological parameters. This is our main discussion today. And sedimentological parameters concerns the particle size. Of course, when you say particle size, in the size is also the shape of the particles, the way of sorting. So how are the particles together in a deposit? So it's not just the size, it's also the sorting, it's also the kurtosis and the shape. Otherwise, we have the organic matter and the carbonate content in sediments that we are measuring, and we have the magnetic properties. So these are the basic three parameters that I will detail further on. Otherwise, we are also interested in the geochemical composition of the sediments and in the paleoecology, because the life from the waters and from the continents, because the sediments in a lake, for instance, capture the life present also in the lacustrine ecosystem, in the, let's say, aquatic, maybe it's a sea, not just a lake, but also the life from the continent, from the subaerial ground. And life with all its features, like species, association of species. It's so important because it's very sensitive to the climate, especially, and to the environment changes. So it's like a royal way to inform, to know, to understand the paleo environment and paleoclimate, using also the paleoecology, the way the life transforms in time. That's why we are using pollen or plant macrofossils or microfauna like Ostracoda and Foraminifera, or even others like chironomids, diatoms. I will not insist, it is not the main subject, but it's important just to have in mind, to have a general and useful picture for you. Otherwise, in the last 2 decades, some new proxies emerged, and they are really powerful. Normally, I will start even with the bottom, with the sedimentary ancient DNA, which I put here, sedimentary DNA, because this tool allows for reconstructing so many species. I will do a comparison from Bula Lake, from Southern Carpathians, that we are working in the present. Using pollen, we identified around 70 species. And after that, using sedimentary ancient DNA, we found 3 times more, around 220 species, including Homo sapiens, of course. So we can track the appearance of the sapiens in a place, the problems, the intensity of its presence, and so on. The other recent proxies that we may use, of course, are the biomarkers. And here we have different kind of biomarkers like branched GDGT, which are very useful for paleotemperature. So it's an important tool in paleoclimatology. Otherwise, we have leaf waxes. Here are alkanone and N-alkans, very useful for the source of organic matter, and stanols, especially the coprostanols and sterols used in geoarchaeology. Stable isotopes, I think everybody heard about stable isotopes, especially oxygen 18. which is also an important tool to reconstruct climate, and the other like carbon-13 or nitrogen-15, which are useful especially for the water masses, for the air masses changes, and many other information concerning the paleoclimate, especially trace elements like the lead or copper, cuprum are important, especially in the geology or in other trace element study concerning the source of that. We'll see now a few systems used, the most used, in fact, used for coring on the water and on the ground. I will start with the water. And here we have different kind of platforms. So floating platforms, you may see two types here from an UVTech, from different UVTech systems. In fact, in the world, most of the teams are working with these two models, Livingstone and UVTech. And these floating platforms are anchored easily in a lake, for instance, or anchored bigger depths with proper anchors. And after that, you have a tripod and a coring piston system, which maybe other using a hammer or manually, or other systems are with an engine pushing here. And after that, you are recovering the tubes. Usually, these kind of tubes are very common, like transparent with 8 or 10 centimeters diameter. This is the classic, and it's a good method of 1 or 1.5 meters or even 2 meters, depends on the manufacturer. Relatively similar for the coring on the ground is the percussion corer method, where you have an engine, a Cobra engine. So like breaking the asphalt road is that kind of engine, but in this case it pushes on an array of roads up to 20 meters depth, and then you have an extraction system, which sometimes it's using engines, sometimes it's using people for extracting these tubes. And in this case, the tubes are narrower, like 5 centimeters the diameter. You may see in the photo here in our lab on the table. And then you need to cut longitudinally these tubes. So you cut on the vertical axis. They will be split in two, like here on this table. The next step is to describe the coring. So it's an sedimentological and stratigraphical basic description, because at that moment you don't have the proper measurements. You have only the visual aspect of the core, and you may touch, you may use also your finger just to assess how coarse or how fine are the sediments, and you may describe like being shingles, coarse, fine, medium sands, or coarse silts, or even clay, or looking at how sticky it is, how blacky. You can also have an idea about the organic matter content. When it is more sticky, more blackish, this means that the clay content is higher, but also the organic matter content is higher. So we have a basic description using this visual inspection, saying what kind of sediments are there for what, and normally should be a table like that that you'll use for have the first graph. You'll see next time some graphs made with this kind of description. After that, we take samples from each unit that you identify in the lab and try to measure all that parameters that we discussed. And finally, not to forget, the carbon dating is very, very important, because all the information that we collect should be interpreted in a chronological framework. So other steps that follows after the sampling in the lab is the grain size measurement. And assessment of the organic matter and carbonates using the loss on ignition method. We have this acronym LOI, loss on ignition. This means it's very easy. You need just a very good weighter, a balance, if possible with 4 or 5 digits, because you need a good accuracy, and also a strong oven, because you need to use 3 temperature thresholds. The first one is for estimate the water content, and for that you need to heat the sediments a little above 100 degree. So the threshold is 105 degree. Then you wait again the sediments. Now you know how much water do you have in sediments. The next threshold, it's 540 degrees for burning the organic matter, and also waiting again the sediment samples. You'll know how much organic matter you have there. And the last threshold, it's 950 Celsius degree for measuring the inorganic carbonate content. Another method, also very good, is the total organic carbon content. It's is this tool here. It's much more expensive, but better for measuring the organic matter content. And after that, there are some simple equations that you may use in the Excel to account for different texture. Texture means grain size properties, parameters, or for organic matter and carbonates parameters. And this is the system that you may use is the most popular in the present. It's an laser diffraction particle size analyzers. You are processing the sediments using different solution based especially on the oxygenate water, and staying a few days for making a solution very uniform. And after that, you take all the approbates, the sediments, and insert in the machine, and the laser ray diffraction assess finally, how I told you, the size of the sediments, the shape, and the sorting. And these are very, very important properties, because you may find information about what happened in the surroundings, knowing the grain size parameters like mean size and sorting especially. For instance, different climate intervals have a clear signature in the sediments with, for instance, wetter intervals will bring coarser sediments. This is like one relation for some lakes. Or if you compare the last glacial maximum, so the glacial intervals with interglacial intervals, you also will have different large differences, especially in organic matter, because all the glacial intervals, the cold intervals, had a very low content in organic matter, while interglacial favored the vegetation spreading, the formation of the soils, and the organic matter will be very different. Also the clay formation, also the geochemistry. So it's important for the climate, but also for the geomorphology per se. Another example that I may give to you, it's using a glacial lake and looking at the coarser sediments, like in this figure, it's a borehole from Făgăraș lakes, and you may see in yellow the sands. Even here in the oranges are the gravels. So this part contained coarser fraction also here and here, and they are also corresponding to poorer sorting values. This means that where events of debris flows and intervals of climatic instability which favored the debris flows to develop in the catchment and bring coarser sediments to the lake. And in red, we put usually the carbon 14 ages. Is a classic method useful here. We have the values of the organic matter and carbonates, but maybe we'll look also at other examples. For instance, in this picture, you may look. So the first was from a glacial lake in the southern Carpathians. Now we are on the lower Danube floodplain with several boreholes. These are the depths, 10, 18, 17, so relatively deep boreholes that we extracted using percussion corer. And just a few words about the way usually the people are drawing these graphs. So the thickness of the graph, so the thick it is, the coarser will be the sediment. So this yellow thick color here means that there are sands. Here, which is a medium size, means are silts, and if it's black, like here, it's clay. And the green is for peat organic deposit. Otherwise, in this case that I will present rapidly, we measured the total organic content. So we measured the organic matter, and which is expressed in red, for instance, and separately using the H-depth modeling, so knowing the chronology of each core, we determined also the carbon accumulation rate, which is in black. Sometimes these values are relatively similar, like for that core. But there are some cases, look at that one, where you have a low total organic content, but a high carbon accumulation rate. So how this is possible? It is possible due to the different speed of sedimentation. In this case, it's true that the organic content was low, but the sedimentation was extremely rapid. And that's why you'll have this kind of values, and oppositely in other graphs. I will also give some examples from Danube Delta, just a few, so not to worry. Here in red, there are the boreholes that we used for reconstructing the evolution of the delta, and in yellow rectangles are the drillings, which were deeper, that we also used. You may see that for the maritime part of the delta, we have just a few boreholes, it's true, but here we could use OSL datings from beach ridges. So we didn't need so many boreholes like in the inner part of the delta. And I want just to show you a comparison using boreholes from the updrift and downdrift unit of a deltaic lobe. In this case, it is the Sfântu Gheorghe lobe, which in this part, downdrift, we call it the northern part updrift because the longshore currents are usually from north to south. These are the resultant longshore currents, and due to the blockage effect induced by the river mouth, by the Sagbekvius river mouth bar, a great part of the longshore currents sediments are blocked here, and this will be sandy, while in the downdrift unit we'll have it oftenly the river sediment, which are much finer. And expression in the morphology is like you could show here. So sandy beach ridges and muddy barrier marsh plain. And after that, if you are looking in the left part, these two boreholes are dominated by sands till 12, 14, 16 meters. There are some variation. While in the downdrift unit here, you may see that there are normally muds and just some sands. Look at, we have an exaggeration of the scale here, double. You could see these are 8 meters, not 16 like in this case. So from 8 below are only clays and seals in that unit. So it's so easy to understand the morphology and the evolution when you know the stratigraphy. That's why the boreholes and the dated boreholes are so useful for the evolution of the systems. And now I'll give you an example of sediment geochemistry, which is also a powerful tool. You can use portable XRF, which means X-ray fluorescence, So this is exactly like an how you call it, pistol, like an you know what I mean, like a revolver. It is looking. It's also useful in the field, in the borehorse. But for the course, it's even better if you use an iTrax system. Here it's our iTrax from Orshova Research Station. It's 5 meter long, and you may put even long course and will the system scanning easily and providing then a worksheet with chemical elements values, intensity in that case, and plotting different elements and especially different ratio. You may found how was the redox activity, how was the size even. For instance, this kind of ratio, it's just an example, zirconium divided to rubidium. It's a very good proxy for the grain size. The difference it is that you may have this kind of scanning in just one day with thousands of values mirroring the mean size, while the measurement in the lab for a borehole of, let's say, 10 meters uh, may cover a few months to have hundreds of samples. So this is the difference. Otherwise, of course, the proper measurements are more obvious than the geochemical index used for that one. And there are so many applications involving geochemistry. I will not insist now on that because we also need some time to speak about pit deposit, because the pit box are different in comparison with the lakes, floodplains, or the marine sediments. So pit box are formed sometimes on the former lakes in some paleo lakes, but not all the time. In mountains, they may appear also in different waterlogged systems, even in the absence of a lake, but usually they are a later stage of a lacustrine system. And the pit bog being fluffy, you need other systems, and the best one, we call it a Russian corer. It's are different roads, and finally you have these sampling systems, which has 60 or 100 centimeters. There are two versions usually. Is this mobile clapet, which is closing. So you are just pushing down the systems from a meter to another meter. If this is of 1 meter, let's say, it's easy because the pit are fluffy, so it's not necessarily to use too much power, and make a rotation of 180 degrees when this mobile clapet is closed. And after that's a 180 rotation, and then you extract all the systems, and that's it. You open it, it looks like here, so it's beautiful. You take after that using different we, for instance, are using some plastic cylinders split in two longitudinally for taking, because all the time you take only half of a cylinder, just half of a cylinder. And of course, you take you may use this lever to extract it, take the position by DGPS, and in the field, in the lab, sorry, it's very easy to date because the pit it's full of organic matter, so it's one of the easiest way to have a good age depth models. And here is an example with different ages, with different ages used for have an age depth model for the Shurano pit bog. And with this material contained in a pit bog, you may use exactly the same steps like for the sediments. But it's true that for the grain size especially, it's a little more complicated because you need first to burn the organic matter. So you start with loss on ignition methods to escape the organic matter and to extract only the minerogenic matter or the mineral matter, we might call it. And this mineral matter, otherwise, it's also easy to analyze in the lab for different grain size parameters and for geochemistry and for everything, even for paleoecology. I will give you also an example from Mangalia, coastal lagoon in southern Romania. Here it's a much shorter core than I show you on the Danube floodplain. And look how diverse are the sediments in this case, because it's an sinkhole, which in the base contains loess. This is a classic loess deposit put here during the last glacial period, which is the last glacial maximum. And after that, in the mid-Holocene, transformed into a lake. Why in the mid-Holocene? Because needed a higher water position, which happened just around 5,000 years ago. So transformed into this sinkhole, transformed into a lake. And after that, we have these sands, which we suppose that were deposited here by two paleotsunamis. And the expression for this unit, only from 3 to 5, we plot it here. So from 3 to 5, you may see the transition from the clays to the sandy units. Yeah, so here it's clay and silts, and then should be mostly medium and even coarse sands. And this is the mean size, so from the fine silts to even clay to sands on the yellow, and this is the sorting. Here it's very good in the sediments and relatively poor in the clays. This is the organic matter, like 8%, then will be less than 1% in the sands, the magnetic susceptibility, and different chemical elements that we are also using for capturing more information about these events. And just an example also for this borehole using microfauna. In this case, we use Ostracoda and Foraminifera. Ammonia beccari, it's a maritime Foraminifera, which show the fresh brackish origin of this coastal lagoon, and then maritime sands that were deposited here, even with some species characteristic to deeper waters corresponding in this case to the continental shelf. But I will not insist on that. I think maybe we'll have also a few minutes for questions. I'm looking at the clock because it's shown here. So thank you very much to all of you, and especially to Nikki, our organizer.
Thank you very much, Alfred. I always enjoying listening to you explaining this subject. We already have a question for you in the chat, so I will read it.
Please.
Asem Salama asks, I would like to ask about indicators in course for paleoclimate change related to the rise or low of temperature.
Yes, so what is better to use to find rise and lowerings in temperatures? The best is the isotope of oxygen, the ratio between 16 and 18 isotope of oxygen. And the problem in sediments, it is that you may not use direct sediments for having these isotope measurements. You need to use either peat. So if you have a peat bog, you may use peat. But if you don't have peat and it's classic sediments, you may use the fauna inside the sediments. And here there are two options. The best is to use diatoms. Diatoms are perfect because their coquina, it's made from silicium dioxide, so it's full of oxygen. But the problem it is diatoms are very, very small, and there are just a few people with this this speciality. So it's not easy to find the lab. We just formed a colleague in this method, and it covers a few years for specialization. The other one, you may also use Ostracoda for having isotopes, oxygen isotopes. So this is the best. Otherwise, you may use pollen. So even from a very good pollen analysis, from a pollen diagram, there are some algorithms, some equations, like the ratio between arboreal and non-arboreal pollen between different species that you may determine temperatures. But in this case, you need a rich pollen analysis with many species and a very small intervals, a good accuracy to may try this. So it's also feasible using the pollen captured in sediments for uh, the trending paleo temperatures. This is just two examples. Certainly, there are also other methods, but I think it's okay for you.
There is one more question for you.
Yes.
From
It's
Elenia
Mishu. Yes, it's
Kidous.
Mishu which also answered. I've seen it, and she's right.
Sorry?
But I think Mishu can intervene directly orally because you are present.
Yes, she has written the question. Maybe, Eleni, if you wish, you may turn on your microphone and instead of me, you can ask directly.
Hi, yes. I would like to ask if the diffraction particle size analyzer can replace the sieving method.
Normally, laser diffraction particle size analyzer replaced sieving method, but not always. So normally it is better for classic sediment. It is better to have directly laser system because you have around 2000 thresholds. So you will have a sedimentological curve very detailed in comparison with the sieving, which are just a few sieves. But for the sediments which are coarser than sands, and even for the coarse sands, so for textures coarser than 1 millimeter, the sieve are necessary to find how many pebbles, shingles, and very coarse sands. For this over 1 millimeter size, you need sieving.
Okay, thank you.
And Michaela has also posted a comment. Michaela, would you like to turn on your microphone?
Yes, I try to complete the answer of Alfred in regarding the possibility to reconstruct temperature in the past in order to determine the environmental conditions. So we can use also, as Freddy already presented in one slide, we can use also biomarkers in order to determine this values, the temperature values in different deposition condition.
Good. Thank you so much. We have also a question about the first speaker, but I noticed that it is already answered through chat. So I will leave it for the end if there is something additional. Okay. And now let's go to the third speaker. François Sabatier is a professor at Aix-Marseille University. He is a coastal geomorphologist specialized in the study of coastal processes on macrotidal beaches, ranging from their long-term evolution to the impacts of storms. His research has notably highlighted the decrease in sedimentary contributions from their own to the beaches, as well as the organization of littoral drift cells along their own delta and the vulnerability of pocket beaches to rising sea levels. You have, for those who joined the first workshop, you have already met him. He's a member of our TRACE project, representing the French university. So, François, the floor is yours.
Thanks. Thanks, Nikki. Just one point. Sometimes, perhaps my PowerPoint is going to disappear. I don't know why. It just happened 20 seconds. Okay, so we start and we will see. So good night. You see my PowerPoint or not?
No.
I should try something else. Okay.
It's coming.
It was the same the last time.
Yes, it is coming, but we can see a black screen for the
Yes,
moment.
and after a few seconds, it's closed. I imagine to have fixed the trouble, but not.
Okay, I can share your presentation if you wish.
Once again.
Yes, but you will have to let me know when you want to go to the next slide, okay?
Okay, this is the dangerous to be online and in live. Well, my talk today, the title is about a simulation, but actually I will speak about a modeling approach because there is several, and probably you need to have some information to find a good way to modelize your system, and it's also necessary because sometimes when you read papers, you don't know exactly what kind of model they use, and I hope that this lecture can be useful for you. So next, please, Nikki. Okay, so we can think and pose and ask this question: what is a model? You can consider that it is a simplified representation of the real-world systems. So when you are using model, the aim is to describe, explain, and predict system behavior. And most of the time, it is not all the time, it's based on assumptions. And these assumptions reduce complexity while retaining key processes. There is several kind of model, and we are looking about them. And in coastal geomorphology, most of the time they are used to represent interaction between waves, currents, and sediment transport, and at the end, morphology. And they can help in the understanding of erosion, sediment transport, and shoreline evolution, and so on. So you should keep in mind that the models do not represent the reality, but it is a tool to better understand and simulate it. And of course, it's connected to field measurement. We will see later because there is several kinds of model. Next, please, Nikki. So during this talk, we speak about conceptual modeling, empirical modeling, physical modeling, process-based modeling, and few words on deterministic versus stochastic modeling and numerical modeling. And I will give some example to give it better, because sometimes it is, I don't know the English words, but in French we said indigest. I guess you understand. Next, please. So the first kind of modeling approach is quite simple and everybody uses it. It is conceptual model. And it's a kind of simplified representation of coastal systems. And you identify key processes, the waves, currents, and sediment transport. And most of the time you focus between the forcing agents and the morphology. This is the first step for quantitative analysis because it is qualitative. So conceptual model, please, the next slide. And the thing is that, yes, you should keep in mind that it is qualitative. And most of the time you are using diagrams or sediment pathway or figures in order to observe the source, the sink, and the storage. And also to define a direction of current, for example, longshore and currents. So some example, the next, please. Yes, this is a conceptual model. For you, you can imagine that it is just a figure, but this is a kind of resume of sediment transport under extreme and modal condition. It is from a colleague on a pocket beach. And each black and red arrows represent direction of currents. And like this, you can understand most the interaction between currents. So this kind of result is quite important to define the organization of your system. This is just an example. We can see another, please, on the next slide. I guess you remember the first, no, not the first, but the video put on the website, and you have to look at it. And I'm speaking about state of the beaches related to right and short terminology. And for example, this one show what we're calling a dissipative beach, and it's a kind of concept. And you see that there is a draw, and you can with that understanding that if the surf zone is very flat, the waves are very small. So we are speaking about a dissipative action process for the waves. And this is typically another example of a conceptual model. The next, please. So we can, this is the same thing, so I should be fast. So the next, please. Yes, another example. In that case, you have a conceptual model of the evolution of a barrier. You see on the middle, on the top, there is the barrier with the lagoon on the left and the ocean on the right. So the paper is about overwash event and outwash event. On the left column, you see that during overwash, the sand is pushed, is moving from the beach, the dunes, to the lagoon, but not exactly in the lagoon. There is a thin layer of sand, and with time, vegetation can appear and stabilize the overwash. Meanwhile, during outwash, which is when the seawater is really, really high and cross the barrier, after that, the colleagues show evidence that there is a kind of lagoon, and because there is a lot of water, there is less vegetation. And in that case, if there is less vegetation, the barrier cannot reduce the erosion by the waves. So this is conceptual descriptions. And after, you can use other model to calculate the transport and the morphology. We will see the next, please. So another kind of approach is what we are calling empirical modeling. Empirical modeling is, let's say, empirical. It's based on observation and statistical relationship from these observations. In that case, the physical processes are not well represented. But there is a large advantage, it's that it is simple and fast. And of course, the trouble is that it is simple and fast, so there is some limitation. And for example, the validity limited to the context of calibration. Most of the time when you are doing empirical observation, empirical modeling, it is, let's say, representative of what you are doing and difficult to extract. And because you try to connect observation, you try to connect, for example, waves and the morphology. At the end, it is also a mathematical approach. So we can see on the next slide. By this example, I will show you what is the depth of closure. You see on this graph that you have a lot of profiles. It is a bathymetric profile, topographic and bathymetric profiles in US. There is several. And as there is several, you see that the envelope of the profile on the upper part are moving a lot. There is a lot of data. And after, along the short distance, after 500 meters, you see that all the profiles on the offshore are connected to each other. There is no variation of this of the profiles. So that means that around 20 foot, because the graph is not in meter, it is in foot, around this depth, there is no significant movement of the bottom of the profiles. So this is what we're calling the depth of closure. Anyway, this depth can be computed by a simple equation, which is down. And you see this equation is quite simple because it is only connected to wave 8, which is HE. And you see on the tail that there is HE, and with well, gravity and with a period. So you see that we can simulate this depth only with these parameters. And this is not completely based on process. It is why we are calling that it is an empirical equation. There is no simulation of the waves, there is no simulation of the current, there is no simulation of the interaction between the waves and the sediment. So this is typically an empirical equation, an empirical approach. So next slide, please. Well, another example of empirical measurements and empirical modeling. You see that on the left, on the pictures, it was 30 years ago, and we were using sediment traps in the surf zone in order to catch the sediment transports. And you see that in the, yes, this one. And in the central part, you see that you put several traps in the surf zone, and after, like this, you can quantify the longshore sediment transport. You measure the weight, you measure the sediment which is moving by the currents, and you can connect it. Have a look on the right. You can connect the sediment transport with the wave energy, because there is a relation between wave energy, which is connected to wave 8, and with the wave angle. You see that this connection is well, for sediment transport is pretty good. So you can calculate with Q, which is the longshore sediment transport in the central part of the slide. You can simply calculate the longshore sediment transport by the use of K, which is an empirical parameter, HB, which is the height of the wave at the breaking point, and sinus 2 alpha B, which is the angle of incidence close to the shoreline and close to the breaking zone. But in that case, it is empirical because all the processes are not described. So the next, please. Another example is what we're calling physical modeling. Physical modeling is in laboratory. You see on this picture that there is a large area where there is water and we are making waves. So next, please. Physical modeling is based on the principle which are a little bit limited, but very useful always, is that the trouble is that you want to simulate, for example, wave storms, but on the field, the waves can be 6, 7 meters, 8, and not in the physical models. They will be most of the time in the maximum 1 meter. So you have to find a scale to translate what's happening in the field on what you do in your laboratory. And it is connected to what we call the food number. We should use food similarity for waves are in the process. And several rules concerning the scaling of sediment transport and morphology. So when you do that, you can have a good result. We can see on the next slide, please. Yes, for example, in this one. You see on the left the pictures, the photographs. There is a large wave flume. You see it is a kind of corridor. There is some water inside, and the waves are pushed in the back, and they are moving in our direction. And what it is nice is that in that case, you can measure and control the wave propagation. You can put some measurements to observe the wave A, wave period, wave interaction, and current, and so on. So you control the system. And in that case, there is several tests in order to understand the cross-shore sediment transport, depending of the slope of the beach. And you see that to explain that, to introduce that, on the right, authors use a conceptual model because on the right, it is a conceptual model to represent all the currents connected to this wave propagation. So just to say that when you are doing modeling, you combine all the kind of approach. So next, please. And when you have a huge large wave plume, what sometimes it's possible to do is, for example, in that case, see that they put some sand and they put some vegetation, and the test is to observe if the vegetation can reduce coastal erosion. You see also on the picture that there is some equipment to measure the wave and the sediment suspension and so on, which is a very nice because you can control large processes. But in the field, it is very often and sometimes different. So next slide, please. Oh, click again, please. Like this, yes. So for example, you can, and you should combine the physical and the experimental observation. For example, in that slide, we are looking about the slope of the beach face. You remember probably what the beach face is. So if you lost the first lesson, the beach face is the part of the beach, you know, where the waves are coming up and down. This movement is the swash zone, and this is the beach face. And the slope of the beach face can be estimated by a simple equation. You see the equation, and on that case, you can compare what you obtain in the laboratory and on the field. You see that there is empirical parameters which are different, but it's possible to simulate both. And we can have a look on the next slide, because the next is the same idea, but in that case, the equation there, which is a mathematical and empirical equation, but it is based on the laboratory and on field observation. You simulate the height of the berm, and the height of the berm, you know that the berm is the part after the swash zone which is elevated, and it's very important to be able to simulate that because if you know that, you can define a level of wave action and submersion during the storms. So you see that in this equation is a kind of modeling approach, but it is mathematical and it is empirical, because the height of the berm, BH, is connected to the height of the wave at the breaking point, HB, and after to the period and gravity. And you just take very few parameters. And this is a kind of a modeling approach. When you have a lot of data, and you see on the graph, is working. So it's very good, and it's very easy to use. And at the end, all this kind of equation can be used for a numerical modeling approach. I think it is the next slide. No, I forgot some things. Yes, sorry, I forgot something. The other point is that you can simulate, for example, sediment transports by the use of a lot of parameters in order to try to integrate all the processes. So this kind of modeling is a little bit quite complex than the previous, and you are describing the process by using equations step by step. The governing equation most of the time focus on hydrodynamics and sediment transport, and what we're calling continuity equation for bed evolution, which is a kind of rule which permit to simulate morphology. Well, we can have a look, please, on the next slide. Yes, an example of a process-based modeling approach. This one is based on Van Rijn. Van Rijn to simulate a bed load sediment transport, and you see that there is several parameters in the equation, and these parameters are connected. I put it in red. They are connected to the grain size. You have to calculate several parameters around the grain size, and after the parameter in the equation is connected to the skin belt shear stress due to current and waves. This is because when the current of the waves on both are moving, they act on the bottom as a stress, and this stress can induce sediment transport. So you have to calculate, compute that, and you need several steps to calculate these best shear stress. You also need, this is the last term of this equation, to calculate what we call critical bed shear stress, which can be simplified as the result between the stress related to the wave and the currents and the sediment size. And between them, there is a critical point, critical value, when the sediment transport is initiated. So you see that in that case, it is not empirical. You focus on the wave first. You have to calculate it or measure it. You focus after the wave to calculate the current. After the current, you calculate the shear stress, and after the shear stress, you calculate the critical bed shear stress, which is connected to the dimensionless sediment parameters. All these steps are what we're calling process-based modeling. And when you compute all this process, you can put all these lines in the numerical model in order to make a faster computation on a large scale, which is the next slide. Well, but first, some point concerning what you can find regarding what it is calling deterministic and stochastic approach. It's very simple. Deterministic modeling is something very simple. There is a fixed relation between the forcing and the response in the equation. I mean that you are using an equation and you say that the wave conditions are like this, and the result by the use of this equation will be this one. So each time you take the same wave condition, you always obtain the same result, which seems to be basic. It's a basic approach and seems to be evident. But the thing is that in the field, boundary condition varies a lot. For example, if you say, okay, I took a storm which is a return period of 10 years, which is 5 meters 8, and I calculate some parameters, sediment transport, for example. But on the field, this 5, 8 is not exactly 5, is around 5. So to simulate that, you can use another method, which is stochastic modeling, which is the next slide. And stochastic modeling, yes. Well, the next, please. The stochastic modeling incorporate variability and uncertainty in the forcing, which is a completely different approach. Statistically, it's quite complex. It's based on Monte Carlo approach. And like this, you can randomize a representation of a wave, climate, storm, and so on. So the output are probabilities, are not deterministic. And it means that as it is probabilities, the results are more difficult to interpret, to analyze, and to discuss. Okay, so we will see now, for the end, some numerical models. But sorry, because I do not have my PowerPoint, so sometimes I forget some slides. So this one is an example of a result on stochastic modeling approach. Well, a few information on the left. On the top, you see the result of modeling the evolution of a profile regarding several actions on the profile. These different actions of the profile are on the left graph. The authors use on this profile simulate the erosion if there is a wall close to the shoreline, if there is a wall, if there is a reef, if there is no wall but only sand, and if there is a reef only. You see that there is the result with a point, and you see that there is a kind of error, which is not error actually, which is the result of the stochastic approach. This is the uncertainty of the result. Okay, thanks. We can move to the next one, which is based on the last. Next, please. Yes. Now, numerical modeling. Be sure this is, I just have a few slides with a lot of figure like this. You can be attracted because I know that it's a long to hear someone speaking minutes and minutes. So first, there is two kind of numerical approach. The first one is what we call reduced complexity models. In that case, the processes are not completely used or not completely defined. There is a lot of simplification. It's nice for long-term studies, decadal to centuries, and the time with your computer is not so big. So this kind of model was very used at the beginning of this century, and after they forget, and now they are coming back because understanding are more accurate. So I do not speak about this one more, but they can give interesting results. I will give some information on process-based numerical models. In that case, physics is well represented, not well, but better represented. You calculate the waves first. After the waves, you calculate the currents. After you calculate the sediment transport, and after the bed evolution. After that, the model is running again to calculate the waves, because the waves are modified by the bed evolution. You calculate again the current, the sediment transport, and the bed evolution. And the model calculates again the waves, the current, and so on. Like this, you may build and have a result of what we are calling a morphodynamics model, because you take into account the forcing agents, the sediment transport, the morphology, and the impact of the morphology on the forcing agents. So there is several examples which are listed here, and we will speak about two examples right now. So next, please. First example, not close, but connected to the Rhone Delta, in the mouth of the Rhone Delta. And you see that at the beginning, you have to define a domain. This domain should be well represented using bathymetry measurement, or sometimes topography as well. So if you have a clear and good bathymetry, the result will be probably accurate. If you are using old bathymetry, the result will be worst, and sometimes completely different than the present day. And you calculate a grid cell, and on each this grid cell, the model is going to simulate by itself what I said before: the waves, the current, the sediment transport, and morphology. waves, currents, sediment transport, and morphology. And in that case, because it is a move area with a fresh flow from the river and the water flow from the ocean, there is a mix between the fresh and the seawater. The salinity is changing. We have to also organize the grid on the vertical, which is on the right figure. You'll see that there is also several grids. So you can imagine how computing is difficult if you have a lot of horizontal and vertical grids. You cannot do that by hand. So it's why numerical models are very helpful. So next, please. And first, in the ideal case, you calibrate. You have to compare the model with measurement on the field. So in that example, you see that, for example, on the top, it is wave 8 through time. And the simulation are in green, measurements are in black. So in that case, even if you see difference, you can consider that for a model, the results are pretty good. So do not imagine that you will have 100% of accuracy when you are using a model. So next, please. Another information about calibration. On the top, this is the comparison between the measurement of flow velocity in the river channel and the velocity modelized by the model. And you see on the bottom that there is a connection between the morphology. You see in Greece, the morphology is from sonar measurement, and there is some larger ripple marks on sound waves, and there is a connection between current direction by the models and the morphology. So it can be a good, we hope to have a good result. Next, please. So with the model, what you can do, you can simulate a lot of situations. Of course, it's always time consuming and you have to focus several simulation. In that example, you see that there is a 3 example and we play with the wave direction, which is indicated in black arrow. And you see that the color represents the sediment transports close to the bottom, related to the wave's action and to the input of the current. And you see that the color is not always the same because of the action of, not the action, but because of the importance of the wave direction and sediment transport and deposit. So it's very interesting and nice to be able to do this kind of simulation. But at the end, the result will be a conceptual model. Next slide, please. Because when you realize a lot of simulation, if you want to resume this simulation at the end, what you can do and what we are doing very often is a conceptual model. So you see that you really need to combine all these approaches, and like this, you can better understand your process. So thank you, but it's not finished. Now we are going to Greece. Next slide, please. Yes, it's a pleasure to present some results from a girl. It was a MSc thesis supervised by my colleague, Nikki Ibelpidiou. And so, Nikki, if you want to give some information after, of course, you can. So probably you know this area in Greece for all the audience, and more or less you know what it is. So the question there is that there is a large bay, and you see on the right the sediment. On the bottom is sandy, but you know, close to the beach there is a Posidonia. Posidonia is well, we will see the result, but have a look that the Posidonia is represented in green, it is a kind of algae, which is not exactly algae, but there is a lot in the Mediterranean Sea, and they protect the beach from the coastal erosion. So in that case, the idea was to use a model to simulate the importance of Posidonia to protect the beach and to reduce current. So what the student did is that she used a model with Posidonia, and she simulates the wave and current action without Posidonia. It is a kind of with or without you Posidonia. Next, please. So in that case, you have to play with the model. So sometimes when you have to play, you have to stay in the rule. And in that case, she decided to change the Manning coefficient. Manning coefficient, if I am to resume, is a kind of coefficient which connect the interaction between the current and the bottom. And there is some scale which give value for the Manning coefficient regarding if you have rock, if you have sand, if you have mud, and if you have vegetation and Posidonia. So you see that on that map on the right. The right is the coefficient of Manning coefficient. The Manning coefficient is different, and you see that it is in grade, so we change the coefficient. So some results. What's happening? Next, please. Well, you'll see that this is the result of the current organization, the current pattern in the bay, with or without the Posidonia. And you see, of course, there is the same storms simulated. You'll see that on the right part, the current, if there is no Posidonia, is very strong, very fast, is faster. You'll see that the value are quite more important. So this is the way to evidence that Posidonia can reduce the current in this part. And let's say that we really need this kind of evidence, but because you cannot do some experiment on the field, you know. On the field, you can put some equipment to measure the current, but you cannot destroy the Posidonia just for fun and to measure the current if there is not. So to use the use of a model can give a very good information to do some simulation. In that case, with or without Posidonia, but it can be if you want to change waves, if you want to simulate different storms regarding to climate change and so on. Well, so I think this is the end. Anyway, this is a yes, thanks. So it's good. Well, we can skip this one. I always put more, and after I adapt what I say. And so what you should keep in mind is that there is several kind of modeling approach, and you should not be afraid by that. And if you are lucky, you can use or you can collaborate to combine all these modeling approach in order to better understand what the other side you focus on. Well, thank you.
Thank you, Francois, very much for this nice presentation. What Francois did not mention about this master thesis is that it was a collaboration between Greece and France. In fact, we co-supervised with Francois, and this is also something very nice that we have achieved through our collaboration, not only in this project, but also in other projects that we work together. We may have students working in more than one university, having more than one supervisor and using more than one laboratory equipment from different universities, which is something a very strong tool for all of you. So please keep that in mind, that our universities give this chance. So I think
If I can add, yeah.
yes.
Yes, you should keep in mind that because of CVs and other opportunities, if you want to join several teams between Romagna, Athens, and Aix-Marseille, it's really possible. But you should, of course, apply to, because there is a process, but it's very possible, and all the teachers here push to that. So I hope, and I know that it is working. That's it.
Very nice. If you have any questions for Francois, it's now the time. If you think later about a question, don't hesitate to write us. I don't see any hand or any question in the chat. Meanwhile, as you may think, I want to mention that next week, next Tuesday, we have our last workshop for this series of workshops. The subject is a little bit different than the previous three. It is dedicated to the science that talk. I mean, we may work a lot as a scientific community, as researchers, but it is very, very important to share the results with the community. So we will discuss how we may share the findings and what we are doing in our research with our students, with our society, with everyone. So we will have 3 talks next week from different aspects. Two of these talks will be from the scientific community, but the third one will be from a journalist. So I would really love to see you again next week. Meanwhile, if you have any questions, don't hesitate to come back to us. Mihaela, would you like to say a comment or something?
I want to remind the students to use the educational resources that we provide for them available on the Open Class platform. They could access the platform using the website of the project or directly using the Open Class link. It is important to create a personal account for registration, but it's totally free, and then you will discover so many additional information that could help you to understand the content that we discussed during this workshop series. So it is pity to have these educational resources available and to not use it. There are video materials. Yeah, please, Nikki.
And we have here in the group tutors from other Greek universities. For example, Katerina Theodorakopoula. I just saw a message from her, just to let them know that they may use the material in their classrooms.
Definitely, yes. These materials were created for students, but can be used for all tutors in order to enhance their activities.
If I can add something, is that I'm sorry, but we are a little bit late, and I think that in 10 days you will have an additional material concerning a virtual trip in the Rhone Delta, as there is a virtual trip in Cephalonia, building and working very hard on it. So I hope that in 1 week or 10 days, the student can go to the Rhone Delta virtually to visit it.
Then they have a lot of virtual trips available already on the platform. So it will be great to have a virtual field trip from France, but there are already available different virtual field trips. So indeed, we will provide even more materials.
Great. So, thank you everybody very much for joining us. See you. Looking forward to seeing you in 1 week from now. Have a nice evening. Thank you.
Thank you. Have a
Thank
nice
you.
evening.
Bye.
Bye.
Thank you. Bye.
Bye.
Thank you.
Bye.